All right, so today we're going to move on to the fundamental theorem of calculus part 2, and we're going to build a little bit on part 1. But I do want to do this introductory exercise. So Nadine is training for her figure skating competition. Her velocity is given by that v of t function for t between 0 and 5. And velocity is measured in meters per second, and t is measured in time. All right, now we're going to use a calculator to do a lot of this. So our number 1, we're going to describe Nadine's velocity over the 5-second interval. So to do that, I'm just going to type it into the calculator. And look at the graph between 0 and 5. Have something weird going on, but I think we should be okay now. All right. So it looks like that her velocity is positive everywhere because it's above the x-axis. So that means she's traveling in the same direction the whole time during that time interval. All right. And then it looks like her velocity is increasing at the beginning. And it looks like it's increasing from 0 to 3. And then she slows down a little bit. Her velocity gets smaller. So velocity is decreasing from 3 to 5. Oh, sorry. Right. And then for number 2, we want to interpret the meaning of the integral from 2 to 5 of the velocity function dt in the context of this problem. So going back to when we first started talking about integration, if we were doing those areas and we were accumulating areas, and remember that if it was a velocity function and it was in meters per second, then we would multiply by the seconds and it would give us meters. So if we are finding the integral of a velocity, that's going to give us the net distance in meters she traveled between 2 and 5 seconds. Right, and then just a side note, if we are finding the integral of the velocity function, that is called the displacement. It gives you the displacement. So how much she changed, her distance changed from where she was at time 2 to where she was at time 5. Now, not the total distance traveled. Well, she is traveling in the same direction, but it's not always that case. So someone could be going back and forth, back and forth, back and forth. So we don't get the total distance traveled, we get the net change. That's displacement. Okay, now there is a way to do these integrals on the calculator, and that is to do alpha window 4. All right, so we're going to find the integral from 2 to 5 of this velocity function by going to the home screen and doing alpha window 4 from 2 to 5, and then I have that velocity function in y1. Okay, so that is 27, and since we did the integral of a velocity, it takes the meters per second, multiplies them by seconds, and so that is 27 meters. So that's how much distance I guess the net change in her distance from time 2 to time 5. Okay, and then for 3, we're going to give a possible position function, S of t, that could represent her position in meters from one end of the rink to the other. So if I want to go from velocity to position, I'm going to do the integral. All right, so I'm going to add 1 to the exponent and divide by my new exponent. So add 1, and that's 2, divide by 2. And then I'm just going to pick a random constant. I'm just going to say 4. All right, and then for number 4, we're going to find the change in position from time equals 2 to 5. So I'm going to do S of 5 and subtract S of 2. All right, so that's just taking that 5 and putting it in for all those t's, and I did that earlier, and I got 42.33333. And I took 2 and put it in for all those 2's, and I got 15.33333. And that is going to be 27 meters. So the answers to question 2 and 4 are the same. So that must not be a coincidence. So that's a new rule. The fundamental theorem of calculus part 2, if we're doing the integral from, we'll say 2 to 5, what you do is you find the antiderivative, and then you plug in the 5 and then subtract, and then you plug in the 2. And we'll write that down on the front in just a second. All right, and then we're going to discover another rule. So at time t equals 2, Nadine is 12 meters from the edge of the rink. So then we want to figure out where she is at time 5. So we can take where she is at time 2 and add how much her distance has changed between 2 and 5 seconds. And that's going to be 39 meters from the edge, because she was traveling in the same direction that whole time. Okay. Another way to write that is her position at 5 is going to be her position at 2 plus the integral from 2 to 5 of the velocity. Okay, and then we'll just use that to find her actual position function. And we did this a little bit yesterday. So I'm going to go back to my one that I made up, but instead of the plus 4, we are going to do a plus c. All right, and then I know that time that S of 2 should equal 12. So you can go back and put 2 in for all those t's. All right, and that's going to give you 11.33333. So when I subtract that, my c is 2/3. So the actual position has the 2/3 in for c. Okay. So the back side of that is going to be your worksheet for your assignment. And then the next sheet, we'll do our notes. Okay, so the fundamental theorem of calculus part 2 is when we're doing a definite integral. So we have upper and lower limits. We're going to do f of b minus f of a, where f of x is the antiderivative, or the f prime of that would give you f of x. Okay, and then the other rule is what we did when we were finding how far away she was from the edge of the rink. If we want to know this final value, we can take something that we know, like an initial value, and add to that the integral from a to b of f prime of x dx. This gives you the accumulated change. Okay, now one thing I want you guys to pay attention to is that these are the same and these are the same. If they're not, you're doing the wrong problem. All right, so let's look at this check for understanding. So the temperature of water in a tub is given by a strictly increasing twice differentiable function w of t, and selected values of wt are given in this table below. We want to evaluate the integral from 0 to 20 of w prime of t dt, and we're going to interpret it in the context of this problem. All right, so we're going to use that fundamental theorem of calculus, part 2. All right, so what we would do is we would do w of 20 minus w of 0. Right, w of 20 is 71, w of 0 is 55, so that's going to be 16. Now we need to talk about the units. This is 16 degrees Fahrenheit. Right, and then what this means is between t equals 0 and t equals 20, the temperature of the water had a net change of 16 degrees Fahrenheit. Now that's obvious from that table that that's what that means, but we needed to find the integral using that table. Okay, for number 2, the graph of g prime is given below. If g of negative 2 is negative 11, find g of 4. Okay, so this is where I'm going to use that second rule. All right, so g of 4 should be equal to g of negative 2 plus the integral from negative 2 to 4 of g prime of x dx. Okay, so paying attention, these two are the same. These two are the same. And this is g prime. This is g. This is g. This is g prime. That all has to fall in line for this to work. Okay, so we can find g of 4 we know g of negative 2 is negative 11. And then we can use the areas to find the integral from negative 2 to 4, because this is the graph of g prime, right? This is a semicircle, 1/2 pi r squared. The radius is 2. So 1/2 pi times 4, that's all that's going to be 2 pi. This is 1/2 base times height, which is going to be 2. So this whole thing is 2 pi plus 2. So g of 4 is negative 9 plus 2 pi. Okay. And then for number 3, we if g of x is the antiderivative of f of x and g of 3 equals 5, then g of 8 equals. So that would mean if g is the antiderivative of f, that means f is the derivative of g. Or f equals g prime. All right, so I can use that rule we were just talking about. We can take the g of 3 and we can add the integral from 3 to 8 of g prime, which is the same as f, which matches up with d. All right. Now, most of the time, we don't use that fundamental theorem of calculus part 1 to do problems like number 1, which we can, but they're mostly to do problems like these next few. Right? So if we want to evaluate the integral from 4 to 10 of 3 dt, what we would do is go ahead and find the antiderivative of 3, which is going to be 3t. Now, if this is a definite integral, we don't do the plus c. We're going to do this little box, and we'll go ahead and put our lower limit and our upper limit on there. Okay, and then we'll take our upper limit and plug it in to our antiderivative, and then minus the lower limit. So that's going to be 30 minus 12, or 18. Okay, same thing on this one. I'm going to go ahead and find the antiderivative. Right, and then plug in 10 minus, and then plug in 4. Okay. So that ends up being 150 minus 24, or 126. Okay. A couple more. All right. That's gonna be t cubed. I'm not sure why we're doing 10 to 4 every time, but it doesn't really matter. We plug in the 10 minus, we plug in the 4. 1,000 minus 64 is 936. Now, some of the ones you're going to have to do might be a little more complicated, so just take it easy, take your time, plug it in. You can use your calculator to check your answer. So like if I wanted to check that answer, I would do the integral from, oh, I did the wrong thing, sorry. From 4 to 3x squared, oops, dx. Yep, and then you can check yourself that way. Okay, and then this last one, I might not do all this just to save on time. So if I want to evaluate this integral, we would go ahead and find the derivative of the sine, which is going to be the negative cosine of t. And then we're going to plug in x squared, and we're going to plug in pi. So negative cosine of x squared minus negative cosine of pi. Now, if you guys remember what the cosine graph looks like, pi is right here. So the cosine of pi is -1, so this ends up being -1. So that's going to be negative cosine of x squared plus 1. Okay. Just depending on if we have time in class, we may do the rest of that, but I want to show you this extension to the fundamental theorem of calculus part 1. So if the upper limit is a function of x, so it's not just x, we're still going to replace t with that upper limit, but we have to multiply by the derivative of the upper limit. So this is what I'm talking about. We have the first fundamental theorem of calculus is the derivative of an accumulation function. But this one, that upper limit is not just x. So we're still going to take whatever that is. I'm sorry, this should be t. We're still going to take whatever that is and put it in for your t. But then we have to multiply by the derivative of that. So for example, if we want to do the derivative of the integral from 2 to x cubed of the natural log of t dt, we would take the t and replace it with x cubed. But then we have to multiply by the derivative of x cubed. All right, so on this one, if I want to find the derivative of the integral from pi to x squared of sine of t dt, I would take the t and replace it with x squared. But then I have to multiply by the derivative of x squared. And most of the time, that derivative comes in the front. Okay. All right, so your assignment is on the backside of that Nadine figure skating thing. And so there are 3 problems to do with a graphing calculator, but then the rest of them I just want you to check, and the rest of them come out of the book.